Continuity, Part 1. The function f of x is continuous at a point A if 1. F of a exists, 2. The limit as x approaches a of f of x exists, and 3. The limit as x approaches a of f of x is equal to f of a. So you need to be able to show all three of these things in order to say that f of x is continuous at point A. Because it's possible for some of these things to be true, but not all three. But in order to have continuity, all three of these must be true. So let's look at a couple different combinations of truthiness for these different criteria, these different hypotheses. So for this one, we have f of a exists, so we have a closed point at a f of a. The limit as x approaches a of f of x exists, but the limit and the output are not equal to each other. So we know that our limit exists, so our left and right limits are equal to each other, but f of a is not equal to f of x, even though it exists, which means that we have some sort of discontinuity here. So this is discontinuous. Let's look at the next one. So f of a does not exist, so that's undefined, but the limit as x approaches a of f of x does exist. And of course, if one of them doesn't exist, they can't be equal to each other. So here we have that our limit exists, but f of a does not exist. This is also discontinuous. Now we have that f of a does not exist, and the limit does not exist. So of course they're not equal to each other. But here we have our left limit approaches one value, and our right limit approaches another value. So our limits do not exist. If for some reason we had f of a exists, but the limits do not, we might have some sort of closed circle. But again, for this one, f of a does not exist. So this is discontinuous. And then finally, we have f of a exists, the limit as x approaches a of f of x exists, and the limit as x approaches a of f of x is equal to f of a. So I like to draw that my limits exist, and then f of a exists, and it's equal to the limit. So we have a nice closed circle here. So we're continuous at A. Could not spell continuous and say at A at the same time. So remember, you need to check for all three of these. It's not enough just to show that they exist, because it's possible that they exist but they're not equal, and then we're discontinuous. So in order to have continuity, we have to show all three of these. Let's identify some discontinuous points. So the first thing that I like to check for are either areas where f of a does not exist or places where the limit does not exist. And rather than just jumping around looking at this whole thing, I like to go from left to right as I search for these. So let's see. If I look at this point, it's the endpoint of a function. So the limit exists. And if I look at it, it's a closed circle. So f of, in this case, -1 also exists. Oh, -2. -1, -2. 1, 2, 3, 4, 5, 6. There we go. That way I don't say the wrong values. So that's not discontinuous. But if I look over here at x is equal to 2, my function is discontinuous because even though I have an f of 2, my left and right limits are not equal. So the limit as x approaches 2 of f of x does not exist. So that's my first discontinuity. And then scanning along my function again, I see another discontinuity. at x is equal to 4 because I could either say that the limit and f of 4 are not equal, but even so, I can say that I can say that just f of 4 does not exist or is undefined because I only have an open circle, I don't have a closed circle. And then again, at x is equal to 6, although my limit exists, f of 6 does not exist or is undefined. So I have 3 discontinuities for f of x. Now let's take a look at g of x. So looking at my function here, I see that at x is equal to 0, I have a discontinuity because the limit as x approaches 0 does not exist. And then I have another discontinuity at x is equal to 2 for the same reason, because the limit as x approaches 2 does not exist. Now we want to state intervals of continuity. So intervals of continuity are similar to the intervals of the domain, but we have some extra criteria here. So this first criteria of continuity, that f of a exists, that is the criteria for a being in the domain. But if we're looking for continuity, we also are looking for points that fulfill these other 2 criteria as well. So it's not enough just to say that f of x exists to have continuity. We also need to show that the limit exists and that the limit and f of a are equal to each other. So what I like to do is look at my graph and just identify any discontinuities. So I have a discontinuity at -2 because my limit does not exist. At 2 because my limit does not exist. At 4 because f of 4 does not exist. At 6 because my limit does not exist. And at 8 because f of a does not exist, or f of 8 does not exist. I am continuous at -4. And then I'm continuous all the way across. Well, that's a little bit too dark. What can I highlight with? Ooh, that's kind of ugly. I guess no highlighting. I'm continuous until my discontinuity at -2. And I have to have this open parenthesis here because I'm not actually continuous at -2. And then I'm continuous from -2 up until 2, where I hit my next discontinuity. And then I'm continuous from 2 to 4, where I hit my next continuity. And then again from 4 to 6, and then from 6, oops, forgot my U, from 6 to 8. This time I have this open parenthesis at 8 because I'm not actually continuous there. I'm discontinuous. But again, I have my bracket at -4 because I am continuous here.